So today, what I'd like to tell you about is how to construct a density of a random variable. Once we have the density of a random variable, we can find out everything we need about that random variable, including its distribution and all the probabilities associated with measurable sets. As always, let's start with the story. The spring rain was falling heavily in the lake above the dam next to the village. Everyone knew that the dam would eventually fail, but when? The wizard began to form a model. If t was the time until the dam failed, then the probability that t was in a short interval near little t days was about e to the minus t times the indicator that t was greater than or equal to 0 times the length of the interval. For example, the chance that t was in the interval from 1.3 to 1.31 was approximately e to the minus 1.3 times 0.01, which was the length of that interval from 1.3 to 1.31. Given this model, what was the chance that the dam would fail during the second day from now? That is, what was the probability that t was in the interval from 1 to 2? Now, the chance that a continuous random variable exactly equals a particular value is 0. So how can probabilities be calculated? One way is to use the notion of a differential, which intuitively means an infinitesimally small change in a variable. For variable x, dx is a differential change in x. For variable t, dt is how the differential is expressed. A differential can also represent an infinitesimally small interval. For instance, use the notation x is in little dx to mean that x is in an interval of length dx that contains the variable x. That is, roughly speaking, x is in dx is the event that x is in the interval from x to x plus dx. So depending on context, dx is either the width of a short interval or the short interval itself, and which one just depends on the context. In the story for today, the wizard's model is that the probability that big T is in d little t equals e to the minus t d little t. On the left-hand side of the equation, the dt is representing an interval, while on the right-hand side, it is representing the width of that interval. Now, the wizard really wants to know the probability that t is in the interval from 1 to 2, not a short interval at all. To get this probability, think about breaking the interval from 1 up to 2 into disjoint little short intervals. Find the probability that t is in each of the short intervals and add back up to get the probability that t is in the large interval. The sum of a bunch of infinitesimal intervals is called an integral, and the sign of an integral is a stretched out letter s for that reason. Overall, this can be written as the probability that t is in the interval from 1 to 2 equals the integral over little t in the interval from 1 to 2 of the probability that big T is in d little t. This is a special case of a far-reaching definition. For a random variable x and a measurable set a, the probability that x is in a equals the integral over little a in big A of the probability that t is in little dA. Now, when the set A is a closed interval from a up to b, then an alternate notation for integration puts the little a as a subscript of the integral sign and b as the superscript. So if I want the integral over the interval from a to b, I write integral with a at the low end and b at the high end for any a less than or equal to b. Returning to the story for a moment, the model gives that the probability that t is in the interval from 1 up to 2 equals the integral from 1 to 2 of the probability that t is in d little t, which is the integral from 1 to 2 of e to the minus t times the indicator that t is greater than or equal to 0 times dt. Now note that the integral is over t in the interval from 1 to 2. Now if I pick any t value in that interval, the indicator that t is going to be greater than or equal to 0 just equals 1. So it can be removed in this integral. The probability that t is in the interval from 1 up to 2 is just the integral from 1 to 2 of e to the minus t dt. More generally, the following rule holds. If I'm integrating over x in the set A, of f of x times the indicator that x is in b times dx. That's the same as the integral that x is in a intersect b of f of x dx. In this way, an indicator function in the integrand can be moved into the limits of the integral by finding the intersection with the existing limits. Now the thing on the right-hand side is called the Lebeg integral. This is a generalization of the Riemann integrals that are studied in a typical calculus class. The good news is that if a Riemann integral can be solved to get a number, then the Lebeg integral has exactly the same value. In this case, the integral from 1 to 2 of e to the minus t dt equals negative e to the minus t evaluated at the upper limit of 2 and the lower limit of 1. The negative flips that upper and lower, and so we end up with e to the minus 1 minus e to the minus 2, which is about 0.2325. Now in the problem above, the indicator function did not do much, but for other problems it might have an effect. Now let's do an example. Suppose that the probability that x is in dx is 1/2 times the indicator x is in the interval from 0 to 2, and I want to know what's the probability that x is greater than or equal to 1.2. Well, our initial integral has x running from 1.2 all the way up to infinity. That's what it means for x to be greater than or equal to 1.2. And then we put the density, the 1/2 times indicator x is in the interval from 0 to 2, inside the integral. Now we can get rid of that indicator by taking the intersection of the interval from 1.2 to infinity with 0 to 2. And of course that intersection will be the closed interval from 1.2 up to 2, leaving the 1/2 as the integrand. That's going to be 1/2 times the length of the interval from 2 down to 1.2, and that gives us 40%. Now suppose that the probability that x is in d little a equals some function of a times d little a. Then we call f of a the density of the random variable. Our formal definition: if the probability that x is in dA divided by dA equals f of a, then we say that the random variable x has density f of a. This is also known as the probability density function, PDF, or sometimes the radon-Nikodym derivative. If x is a continuous random variable, we say that this density is with respect to Lebeg measure. A subscript indicates which random variable the density is for. For instance, we write s of capital X for the density of capital X and s of capital Y for the density of capital Y. The name of the function for the density usually comes from near the beginning of the alphabet, so f sub x, g sub x, h sub x are all common choices. An alternative notation for the PDF of a random variable x is just PDF sub x. Recall that the probability that x is a real number equals 1 always. It is possible to check that this holds for the two densities that have been seen so far. If I is the integral as t runs from negative infinity to infinity of e to the minus t times the indicator that t is greater than or equal to 0, then that's equal to the integral of t greater than or equal to 0 by bringing the indicator function down to the limit of e to the minus t dt. Now that equals negative of e to the minus t running from 0 to infinity. Of course, when we have infinity as one of our limits, what that really means is that we're taking the limit. So this is the exponential function applied to 0 minus the limit as a goes to infinity of the exponential function applied to negative a, which is just 1. Now, for f sub y of s equal to 1/2 times the indicator that s has to be from 0 to 2, we can find that using the integral as t goes from negative infinity to infinity of 1/2 times the indicator t runs from 0 to 2 of dt. Note that using t there instead of s, as was used earlier, is perfectly fine. I could have used any variable name in my integration. That, of course, using the indicator again to change the limits, is going to be the integral from 0 to 2 of 1/2, which is 1/2 times 2 minus 0, or just 1 again. Now, sometimes a non-negative function has an integral over negative infinity to infinity that is finite, but the integral is not 1. Such a function is called an unnormalized density. So we're going to call g greater than or equal to 0 an unnormalized density if when we integrate g of x dx over all x real numbers, we get a number that's strictly greater than 0, but also strictly less than infinity. We're going to call the inverse of this integral the normalizing constant. And if we take the original function g and divide by its normalizing constant, we're going to get what's called the normalized density. For example, what is the normalizing constant for e to the minus 3t times the indicator that t is greater than or equal to 0? Well, to find the normalizing constant, solve the integral. C is the integral as t runs from negative infinity to infinity of e to the minus 3t times the indicator t is greater than or equal to 0. We can bring the indicator into the limits to say that this is the integral as t runs from 0 to infinity of e to the minus 3t. Anti-differentiating brings down a negative 3 to the denominator, and so we need to evaluate e to the minus 3t over negative 3 as t runs from 0 to infinity. We can get rid of the negative by evaluating at the lower limit first. When I plug in t equals 0, I get 1/3, and then I'm subtracting the limit as b goes to infinity of e to the minus 3b over negative 3. As b gets larger, e to the negative 3b gets closer and closer to 0, and so that limit is just 0, leaving us with 1/3 as the normalizing constant. Now, in fact, that tells us that the normalized density is our original density divided by 1/3, and so our normalized density is going to be 3e to the minus 3t times the indicator that t is greater than or equal to 0. Now, often the CDF is known, and it would be nice to find the PDF. Or sometimes the PDF is known, and it would be nice to find the CDF. Recall for a random variable x, the CDF of x at a is the probability that x is less than or equal to a. So to move from a PDF to a CDF, just integrate. For a continuous random variable x with an integrable PDF, the CDF of x at a is the integral from negative infinity up to a of the PDF of x at r dr. For example, suppose that y has PDF of y at s equal to 3e to the minus 3s times the indicator that s is greater than or equal to 0, and we want to find the CDF of y. Well, for a less than 0, the answer, which I'll call I sub minus, is the integral as s goes from negative infinity up to a of our integrand, including the indicator that s is greater than or equal to 0. So if I bring that down, now we have s in running from negative infinity up to a, intersection 0 to infinity, and that's just the empty set. So that integral is going to be 0. And this is just another way of saying that what the indicator does is it restricts the random variable to be in a certain value. So if I have indicator s greater than or equal to 0 in the PDF of y, that means that y as a random variable has to be greater than or equal to 0. The interesting case is when a is greater than or equal to 0. At that point, the intersection between negative infinity up to a and 0 up to infinity is going to be 0 up to a. And so we can go ahead and anti-differentiate and evaluate, and we find that we're at 1 minus e to the minus 3a. So when we write down the solution for what the CDF actually is, we're going to take that quantity, 1 minus e to the minus 3a, and multiply it by the indicator that a is greater than or equal to 0. Given a CDF, what's the probability that x falls in the interval from a to a plus dA? Well, if I look at negative infinity up to a and the half open interval from greater than a up to a plus dA, those are disjoint intervals whose union covers the interval from negative infinity up to a plus dA. Therefore, the CDF of x at a plus the probability that x is in dA is the CDF of x at a plus dA. Rearranging, we get the probability x is in the interval dA is the CDF of x at a plus dA minus the CDF of x at a. And now we can divide both sides through by dA to get that the PDF of x at a is a fraction which looks a lot like a derivative. And in fact, that motivates the following fact. It's not really a proof, but it gives us an idea of why the following fact is true. If you want to find the PDF of x at a, and if x has a differentiable CDF function, then the PDF of x at a is just the derivative of the CDF of x at a at all but a countable number of values of a. Sometimes a CDF won't have a derivative everywhere. It'll have some sharp turns in it, but that will generally only happen at a finite or a countably infinite number of values. So the key to differentiating an expression with indicator functions is that when the indicator function is 0, the derivative is 0. And when the indicator function is 1, the derivative is just the derivative of whatever function multiplies the indicator function. In other words, indicator functions can be brought out of the derivative operator. If f of x is a differentiable function, then the derivative of the quantity f of x times the indicator that x is in a is just the indicator that x is in a times the derivative of f. For example, suppose that y has CDF. CDF of y at a is a times the indicator that a runs from 0 to 1 plus the indicator that a is greater than 1, and we're asked to find the PDF of y. Well, this CDF is differentiable everywhere except at a equals 0 and at a equals 1. The reason for that is that the graph is 0 until we get up to 0, then it starts taking off at slope 1 until we reach 1, and then it flatlines at 1 and stays 1 thereafter. So it has a derivative, just not at 0 and not at 1, where it makes a sharp turn. But differentiating using the rule for indicator functions just tells us that we can bring the indicator that a is from 0 to 1 out of the differentiation. And of course, the derivative of a is just 1, and the derivative of 1 is just 0. And so we're just left with the indicator that a is in the interval from 0 to 1 as the PDF of y. So that's the story of densities of a continuous random variable. By using integration, we can use the density to find the distribution function of the random variable. See you next time.